Welcome to this explainer. Today, we're diving straight into the analytical chaos and tearing down the complexity of the statistical decision tree. Let's jump right in.
Open any statistical software like Minitab, and you are hit with the dizzying menu of dozens of different hypothesis tests. For many project leaders, this is the exact moment panic sets in. They ask themselves, which test do I choose and when? If you pick the wrong test, your p-value is a lie, your conclusions are garbage, and your project fails. But structured data analysis isn't a guessing game. It follows a strict, logical decision tree. Once you know how to look at your data types and distributions, the data itself will tell you exactly which test to run.
All right, Section 1, Testing for Relationships.
Okay, let's dive into this. When you've got two sets of continuous data, it's kind of like a giant puzzle, and you generally have two main tools to solve it. First up, correlation. Correlation is absolutely fantastic for spotting a trend. It tells you the strength and the direction of a relationship between two continuous variables. Like, as temperature goes up, does humidity go up too? But remember, correlation absolutely does not imply causation. It just tells you they move together. Now, to actually take the next step, we use linear regression. This is where you build a predictive mathematical model. You're literally saying that a continuous input, x, actively drives a continuous output, y, using that classic equation, y equals b0 plus b1x. So you use correlation to spot the trend, but you use linear regression to actually predict the future.
Moving right along to Section 2, Variation and Means.
Right here, we have a brilliantly simple binary choice when testing for variation. Now, in statistics, variation is just a measure of how spread out your data is. If you want to compare the spread between exactly two independent groups, say you're looking at machine A versus machine B, you use the two-variance test. It really is that straightforward. But if your operational reality is a bit more complex and you've got three or more groups where you need to compare their means simultaneously, well, you automatically upgrade your tool to ANOVA, which stands for Analysis of Variance. So, two groups, two-variance test. Three or more groups, ANOVA is your tool.
Now, what's really interesting about this slide is how strict the rules of mathematics are regarding the shape of your data. When comparing the average performance, the means, of two independent groups, you hit this massive fork in the road. We call it the normality divide. If your data forms a beautiful, perfectly symmetrical bell curve, it's normally distributed, and boom, you unlock the two-sample t-test. I love calling this one the parametric king because it is incredibly powerful and precise. But hey, reality is messy, right? Sometimes your data is heavily skewed. It completely fails the normality test. If that happens, the parametric king steps aside, and you must use the non-parametric alternative, the Mann-Whitney test. Because your data is skewed, Mann-Whitney compares the medians instead of the means, ensuring your conclusions aren't corrupted by a few massive outliers.
Section 3, Discrete Proportion Tests.
What happens when we leave continuous measurements behind? When you're just counting categories, like pass or fail, day or night, you are entirely out of the realm of t-tests and regression. Instead, your go-to statistical engine is the chi-square test. You use this when both your input, your x, and your output, your y, are discrete categories. So if you want to know, say, if there's a significant dependency between which shift is working and the type of error being produced, the chi-square test analyzes those categorical counts and gives you a definitive answer.
Section 4, Blueprint RM Logistics in Action. Let's make this real.
Here is our first puzzle, and it's a big one. The black belt wants to know, is the new packaging line genuinely faster than the old one, or are we just seeing a fluke? How do we actually prove it without just guessing?
We follow the exact binary logic we just learned. We're comparing the continuous cycle times of two distinct groups, the old line and the new line. If we plot those cycle times and they form a perfect bell curve, we run our two-sample t-test to compare the means. But, and this is huge, what if the new packaging line has a few massive jams that just heavily skew the data? We instantly recognize it's no longer normal, so we default straight to the Mann-Whitney test to compare their medians instead. Following this rule literally stops you from making a multi-million-dollar mistake based on a few weird data points.
Let's move briskly to our next operational puzzle. We contract with three competing logistics partners, and we need to know exactly how their average transit times stack up against each other.
So the crucial point is right there in the number, 3. We're measuring a continuous variable, transit time, across three distinct groups. Because we have three or more groups, the decision tree automatically points us to an analysis of variance, or ANOVA. This test is going to tell us, with absolute mathematical certainty, if one courier significantly deviates from the pack. That's the exact leverage we need for our next contract negotiation.
Now for scenario C.
This is your classic predictive staffing problem. Can we accurately predict the total packing time required simply based on the exact volume of items in a specific order?
Look at our variables here. Because both our input, the number of items, and our output, the packing time in minutes, are continuous numbers on a scale, we know exactly what to do. We build a linear regression model. We map out the historical data to find our equation, and suddenly, we aren't just guessing how many workers to schedule tomorrow, we are mathematically predicting our daily staffing needs based on incoming volume. It's a real game changer.
Finally, let's look at scenario D. We're seeing a spike in errors on the floor, and we want to know, is a specific day of the week significantly tied to the type of picking errors we're seeing?
And this brilliantly illustrates our final pillar. Just look at the variables. Our input is the day of the week, Monday, Tuesday, Wednesday. Those are discrete categories. Our output is the error type, wrong item, missing item, damaged item, also discrete categories. We aren't measuring decimals here, folks. We are literally counting buckets. Matching a discrete X to a discrete Y leads us right back to the chi-square test to find out if Mondays are actually cursed or if it's all just statistical noise.
Section 5. The Master Technician.
You know, the true power of this entire decision tree is that a black belt does not need to be a pure mathematician to be dangerously effective with data. You just become a master technician. You simply look at your X, look at your Y, check the distribution, and pull the exact right statistical tool from the box every single time. By following this structured roadmap, you absolutely guarantee that your boardroom decisions aren't based on gut feelings or panic, but are backed by bulletproof mathematical justification.
Thank you so much for joining me as we completely deconstructed this analytical roadmap. Now get out there and let the data do the talking for education and entertainment.